Problem 16. The DC power plug allows power to be supplied to an Arduino Uno when it is not connected to a computer. The power plug can accept. This is one of those factual questions. You either know it or you don't. Turns out that the Arduino can accept any voltage. That should be letter B and C. Any DC voltage in the range 7 to 12 volts. Okay. The next question says, based on number 17, based on your answer to the preceding question. So no matter what you chose there, you should be able to make a combination of these batteries. It says, based on your answer to the preceding question, add wires to the following schematic so that the positive and negative terminals have sufficient input voltage for an Arduino Uno. In other words, what happens if you take AA batteries? They have an output of 1.5 volt, and this was the plus minus terminals to the power supply of an Arduino. So you're going to, we know the answer is here 7 to 12, but whatever you did, you should be able to come up with an answer that's consistent with this using these batteries. So we have 1, 2, 3, 4, 5, 6, 7 batteries. If we took 7 batteries of 1.5 volts and added them end to end, remember, just as an aside, if this is a battery and this is the plus and minus end, and I have another battery, plus and minus end, if I hook them up this way, the voltages add. It's just Kirchhoff's voltage law. So that's what I want to do. I want to stack them end to end, 1.5 plus 1.5 dot 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 until I add up to at the least 7 volts. So 5 of these, 1, 2, 3, 4, 5 of these would give me 5 times 1.5 is 7.5 volts. So the bare minimum of 5 of these. So I connect the plus of one to the minus of another, and essentially, you know, that's what I've got here. I just keep doing that, the plus of this to the minus of that. So now I have I have the difference between here and here. This is plus 1.5, 1.5 more is 3, 4.5. So I want to do 2 more. This becomes the plus terminal, and the minus has to snake around somehow. Let's take it all the way around here. So now I've got 1.5 plus 1.5 is 3, plus 1.5 is 4.5, plus 1.5 is 6, plus 1.5 is 7.5. So this arrangement gives 5 times 1.5 equals 7.5 volts, which is sufficient. Remember, the Arduino has a power regulator, a voltage DC power regulator that takes the voltage and makes sure that it is suitable input as long as the input range is 7 to 12. So I could have stretched this out. I could have added another one. That would make it 9. I could have added all of them, and that would have been 10.5. Problem 18. The Arduino program to the right is supposed to cause an LED to blink. The electrical circuit, which isn't shown, is correct. So it's connected to a correct electrical circuit, and the power from the circuit and the power for the circuit is connected to digital pin 9. So we're going to power an LED circuit with digital pin 9. When the program to the right is running, the LED is on continuously. LED is on continuously is what's happening to this. Suggest a change to the program that will cause the LED to blink. Hint, the best solution, one that gets the full points available, involves just one line of code. More complex solutions that also work may earn less than the full points. So what I'm doing here is I'm trying to steer you to the correct answer, or to a correct answer. So let's look at what's happening in this program here. There's a setup and a loop. So these are the necessary parts of the program. We tell pin 9 that it's going to be used for output. That's consistent with the problem statement. Over here it says that its circuit is connected to digital pin 9, so that's correct. That's working. In our loop function, we set pin 9 high, we wait 1000 milliseconds or 1 second, and we set pin 9 low. So pin 9 is high, pin 9 is low, and there's a wait between them. Now it might take a bit to think this through, but what happens here is that the loop ends. This loop function, remember, is being called by this invisible off-screen program. So loop just keeps being repeated, repeated, repeated. So when loop ends, digital write is high, but as soon as loop starts again, it's turned high. So at the end of the loop, digital pin 9 is set to low, but there's a very short delay before it's set to pin high, set to high again. So if I simply, all I have to do here is insert another delay. Let's say 1000 again. That's all you need. So that will cause the pin to be high, wait 1 second, low, wait 1 second. So that's the on and off cycle, and the off cycle is held for 1 second as well. Then the loop gets executed again and the pin goes high. Problem 19. Material X has an atomic weight of 58 grams per mole and a density of 7.8 grams per cubic centimeter and has 2 valence electrons. Compute the number of valence electrons in 0.01 cubic centimeter of material X. So we've got a cubic centimeter and we've got the density. So from these two, we calculate the total mass. Once we know the total mass and the conversion from mass to moles, we can compute the number of moles. So we're left now with the number of moles. Well, moles is Avogadro's number. Avogadro's number relates the number of quantities of something per mole. In this case, it would be atoms. So we have the number of atoms per mole if we use Avogadro's numbers, and then because we know the number of valence electrons per atom, we'll compute the total number of atoms. Let's write that down. Let's write that down in a more systematic way. So the number of electrons equals 2 times the number of atoms. The number of atoms equals Avogadro's number times the number of moles. So the number of atoms we need over here. So, and then we can find the number of moles from the density. Number of mole of this substance is equal to volume times the density times 1 over the molar mass. And this is the mass of the sample. So how do you know these things? Well, these are just definitions, really. Avogadro's, I'm saying D, Avogadro's number and number of moles. So I'm going to work backwards in my computations. The number of moles is equal to the volume times the density, which is equal to 0.01 cubic centimeters times 7.8 grams per cubic centimeter times 1 over the molar mass is 1 mole per 58 grams. Now, carrying units is really smart here because you can check your work. Centimeters cancel, the grams cancel, and we're left with moles. And the answer here is 1.345 times 10 to the minus 3 mole. Okay. Work next step, number of atoms is this many mole. 1.345 times 10 to the minus 3 mole. I'm following my my formulas up here, times Avogadro's numbers, 6.22 times 10 to the 23 atom per mole. Do the computation and you get 8.365 times 10 to the 20 atoms. And then finally the number of electrons, the number of valence electrons is equal to 2 times the number of atoms, 8.365 times 10 to the 20 atoms, or 1.67 10 to the 21 electrons. So that's the answer. Put a box around that. And we could convert that to coulombs and we'd get 269 coulombs.